As promised in my previous videos, here is a practical example of what happens with voltage drop along long feeders to a water pump.
The equivalent load resistance of a 100-watt light bulb, which is essentially just a resistor that emits light and heat, is given by this equation. Plugging in the actual values, if the light bulb is connected to a 110-volt power supply, the equivalent resistance would be 121 ohms. I am making one other change to our circuit. And that is, I'm going to change each of the individual resistors, R, to 0.25 ohms. That means the calculated circuit current will be 110 volts, divided by the total resistance of 2.5 plus 121 ohms, which equals 0.89 amps. With that amount of current flowing in the circuit, the voltage drop across our light bulb will be 0.89 times 121, which equals 107.8 volts. Because the light bulb was rated at 100 watts, which was calculated for a supply voltage of 110 volts, the physical makeup of the light bulb has not changed. Which means our calculated resistance also has not changed. It is still 121 ohms. In our circuit, the voltage drop across the light bulb has been calculated at 107.8 volts, and the current in a circuit has been calculated at 0.89 amps. Therefore, the light bulb will be dissipating 95.9 watts. This means that the output light will be reduced in brilliance by about 4%. The total resistance in the circuit of 121 ohms is the same as connecting a power source to the light bulb with a length of number 14-2 AWG copper wire. This points out the fact that even copper wire has some resistance, which does become significant over some distance. Although a 4% drop in light bulb brilliance is not that significant. Given more light bulbs, or more length of wire, the percentage drop across each light bulb will decrease, to a point where it starts to be significant. This becomes even more significant if the load were a motor, such as a water pump, because the voltage drop across the pump is made up of both resistance and back EMF. The back EMF of a motor is related to its speed of rotation, which is related to the applied voltage, so the drop in voltage is not just 4%, as in the case of a pure resistive load. Instead of the load being purely resistive, let's replace it with a motor whose back EMF and internal resistance provides the same voltage drop as the 10 ohms load did. This means that the voltage drop will be greater than 4. Which ultimately means more current is going to flow for the same amount of work that is being done over time, and depending on that time. This means the windings of the motor will begin to heat, and ultimately overheat, causing damage to the motor. Taking into consideration the characteristics of a motor, the reduction in voltage may mean that the speed of the motor does not have enough energy to get past the inrush current, exacerbating the whole situation even more. This information, as well as other related electrical blogs, may be found on my website at https://www.getpspt.com. There you also have access to my courses, which are continuously being added to, and at the present time include the following.